Swayam Prabha. Digital India. Educated India.
We have discussed in detail the acceptable wave functions of hydrogen atom, and we said that these are called orbitals. For the umpteenth time in this course, orbitals are acceptable solutions for acceptable 1 electron wave functions, acceptable solutions for Schrodinger equation for a 1 electron or hydrogenic systems. So, we have learned how to plot them, we have learned how to draw 3D and contour diagrams like these, and we also said what happens when you draw with pen and paper qualitative sketches. That also we learned that you draw the nodes first, and then every time you change a node the sign must change. That is how. So, what you see here, I am sure you remember, is a 3D depiction of 3 pz orbital along with the contours. And now the question that arises is, we have put in so much of time and effort to learn about atomic orbitals. Of what use are they? I mean, it is not as if we want to only study hydrogen. Hydrogen is the simplest atom. We want to talk about atoms with many electrons, we want to talk about molecules. So, of what use are these simple 1 electron wave functions? Are they of any use? As we will discover, they are of some use, a lot of use, at least at a starting point. Eventually, of course, when things get more complicated, we move on, and we move on to more complex systems, more complex solutions. But to start with, atomic orbitals actually have an important role to play, and for a lot of chemists, orbitals actually make this very complicated quantum mechanical business very simple, because they can be presented in the form of pictures, and you can develop qualitative theories just based on the symmetry of orbitals, what kind of distribution is there in space, and so on and so forth. So, orbitals are actually very important in chemistry. So, we start our discussion now about multi-electron atoms, and there the first approach we will discuss is orbital approximation. So, what you see here is a very popular depiction of multi-electron atom with your 3 electrons, you have a nucleus. Of course, this very good looking picture is from Bohr-Sommerfeld model. So, right now it is not really state of the art, but it finds use in depiction of science in many different platforms. I leave it to you to find out which major government agency has this picture, or at least its adaptation in its logo. So, but to continue our discussion, we have learned what sense to make of the surface plots, and one thing that I should say before moving out from this topic is that very often you see pictures like this, and they are useful, as I said, because they present a qualitative picture. But please remember that what you see here most likely is the region of space in which finding the probability is maximum. So, you decide how much of probability you want to include. As we have discussed earlier, it is not only radius, theta also matters. Phi does not matter because you get rid of phi when you generate real orbitals. So, theta also matters, and from theta and r you can figure out at what r and what values of theta what kind of probabilities are there, and you can construct the surfaces which contain the maybe 90%, 95%, 99% of probability. And additionally, what you do is you show the charge of the sign of the wave functions on the appropriate lobes. But please remember, these are not really orbitals, even though they are called so. They are qualitatively similar looking, but these are regions of space. Okay? Orbitals, as you know, are actually 1 electron wave functions. Okay. And one danger of this is that very often you see popular figures like this, where earlier one was orbital outer structure, this one is inner structure. The purpose is to show the nodes and all, right. In fact, you can buy structures made of styrofoam using this. There is a chemical Journal of Chemical Education paper in which it says how you can cut open a styrofoam structure to actually see the nodes. The problem is, if you depict like this, L equal to 1, M equal to 1, one might think that M is equal to 1 here. That is not what the meaning is. The meaning is these real pictures that are there for n equal to 2, 3 and so on and so forth, they are all generated by taking appropriate linear combinations of m equal to 1 and m equal to minus 1 orbitals. Because as you understand, e to the power I m phi, that is the phi part. So, you cannot really draw an imaginary function in real space. Same is true for say L equal to 2, m equal to 1, L equal to 2, m equal to 2. If you just take m equal to 1 or m equal to minus 1 or m equal to 2, m equal to minus 2, they are imaginary functions. These are actually linear combinations that you get, right, and that is how you generate them. So, please remember that. I hope we will have no confusion about what orbitals really are and what these pictures really are from this point on. But now we come back to our disturbing question. Hydrogen atom has 1 electron, fine. First of all, why will we even bother to spend 3 modules on so many orbitals? Of what use are they? And the answer is that hydrogen has 1 electron, true. It occupies only 1s orbital in the ground state, true. But do not forget, one of the origins of quantum mechanics is hydrogen spectrum. The moment you talk about spectroscopy, you get involved with excited states, which means somehow you have to promote that electron from 1s to maybe, well, whichever orbital the energy takes it to. And then if it is emission spectroscopy, it has to come down. So, if you want to talk about excited states, you better know about the wave functions that are involved in the excited states, and without them you cannot really talk about spectra. And what we are going to discuss now is these orbitals with a little bit of adaptation can actually be used for many electron atoms as well to some extent, and you already know that without me having to tell you so. What is the configuration of helium? You will say 1s2. How? 1s is an orbital, 1 electron wave function. So, how is it that for helium you are saying 1s2? Lithium, beryllium, nitrogen, oxygen, if I just tell you the element, you will be able to rattle off the electron configuration like 1s2, 2s2, 2p3, so on and so forth. How is it that this 1s, 2s, 2p, 3s, 3p, 3d, 4s, how is it that these 1 electron wave functions are being used happily in talking about electron configuration of multi-electron atoms? How is it that we talk about sp hybrid orbitals when we talk about bonding? There are many electrons in molecules anyway. That is what we will learn slowly. Okay. To start with, let us keep things as simple as possible. Let us start with helium. Helium is the simplest many electron atom that one can think of, and if I draw a very rough model of helium, we always start from there, we draw simple pictures. Here we have the nucleus, this is electron number 1, this is electron number 2. Do the electrons know? Do the electrons know that they are number 1 or number 2? No, they do not. Electrons do not wear jerseys, electrons do not have numbers written on them. We are putting the numbers for our convenience so that we can formulate the problem, but electrons are actually indistinguishable. We are going to come back to this point several times later in our discussion. But right for now, this is what you have. You have this position vector of electron number 1 R1, position vector of electron number 2 R2, or you can just think separation, and separation between the two is the vector sum of R1 and R2. Here we have written R1 minus R2, okay. Not really vector sum, we subtract one vector from the other, okay. So, how do we write the Hamiltonian for a system like this? For any quantum mechanical problem, what you need to do is you need to write the Hamiltonian, then you need to think if you can write the wave function in some way, then you can think of how you can solve it, okay. So, this is what the Hamiltonian is going to be. I have shown you the entire thing at one go, but every term is actually labeled with a different color. Let us go one by one. The first term we have written is minus h cross square by 2 mn del capital N square, capital N for nucleus. This is the term for the kinetic energy of the nucleus, and as you can well imagine, understand that we can do separation of variables, so that we can express things in terms of center of mass coordinates and relative coordinates. This kinetic energy of nucleus will be expressed completely in center of mass coordinates and we will not worry about it. The second term, of course, see I have written it this way, you can write it in any order, does not matter. Okay. Second one that I have written is minus h cross square by 2 me, me means mass of electron, del E square, okay. That is I think sorry, this is del 1 square. So, this is the kinetic energy of electron number 1. Next one will be exactly the same thing, except for the fact that instead of 1 we have written 2. What about me? Does me change? No, they do not, the electrons weigh the same. Mass is the same for both the electrons. So, you do not write me1 and me2, makes no sense. But you have to write del 1 and del 2 because x1 y1 z1, x2 y2 z2, these are distinct, r1 r2 these are distinct. Great. So far we have kinetic energy of nucleus, kinetic energy of electrons, kinetic energy electron number 1, electron number 2. Then you have to think of the attraction between nucleus and the electrons. First one minus 1 by 4 pi epsilon 0 Zn nuclear charge E square divided by R1. This stands for attraction between nucleus and electron 1. Next term is exactly the same, once again 1 replaced by 2. So, attraction between nucleus and electron 2. There is a typo here, it is not electron 1, electron 2, please correct it yourself. So far so good. This is just an extension of what we did for hydrogen. Now comes the additional term. The term is E square divided by R1 2. This stands for repulsion between electron number 1 and electron number 2. Okay. As we will see, this becomes a major player and major headache in the subsequent discussion, and a lot of our efforts go into how to account for this. Great. So, what you do is first of all you separate the nuclear and electronic coordinates, and while doing that you write the terms in electron number 1 together, write the terms in electron number 2 together. So, write instead of 1 by 4 pi epsilon 0 like what we did in hydrogen atom, we write Q and this is what we get. Out of this, the first term is basically the nuclear Hamiltonian, do not worry about it, we only worry about the electronic part of the Hamiltonian, and that is because the Hamiltonian for the nuclear part operates on the nuclear part of the wave function. You take the wave function to be a product of a nuclear part and electronic part like in hydrogen atom, and you just do the separation, exactly same treatment as hydrogen atom. So, we will not discuss it again. What we now start worrying about is this electronic part of the Hamiltonian for helium atom. Okay. How many terms do you have? 1, 2, 3, 4, 5. First term kinetic energy of electron 1, second term potential energy of electron 1 due to the nucleus, third term kinetic energy of electron 2, fourth term potential energy of electron 2 due to the nucleus, the last term is what you would not get in our electron system, the electron repulsion. Great. So, I have labeled the terms in 1 and those in 2. I cannot put label here, I mean I can, but it has to be a different color because this R1 2 involves coordinates of R1 as well as 2. So, cannot be separated so easily. So, what you see is that the first one, this one is essentially a 1 electron Hamiltonian for electron number 1, is not it, minus h cross square by 2 me del 1 square minus q z n E square divided by R1, exactly what we had encountered in hydrogen atom, and the second one is also exactly the same as what we encountered in the hydrogen atom, but for electron number 2. 1 electron Hamiltonians, which is sort of a relief. But then what we need to also understand is that see these Hamiltonians are all operating on wave functions that are more complex than what they were for hydrogen. So, each wave function here say let us take the first one psi e, this is a function of not only r1 theta 1 phi 1, it is also a function of r2 theta 2 phi 2, because that electron repulsion is there, right. 2 electrons are there, same charge, they will repel each other. So, we have more number of coordinates in these systems, right. To simplify, what we do is, to start with, we invoke what is called orbital approximation. See, we have learned about atomic orbitals with so much of great effort. So, it makes sense for us to try and retain them to the maximum extent possible. So, what we do is, we write the wave function of any of these as a product of two 1 electron wave functions, electron number 1, electron number 2, and if you had n number of electrons here, we would have written it as product of phi 1, phi 2, so on and so forth, phi n. Okay. We can always write products, as we have discussed while talking about separation of variables earlier. These are in different dimensions, you cannot add them, but you can take products, and the good thing is, since Hamiltonian is a derivative, Hamiltonian contains a d2 dq2 kind of term, you take derivative, then derivative of products, as you know, is a sum. So, the eigenvalue energy nicely separates into different parts also, but will it separate here, we will see. Okay. So, this is where we are. Now, what I have done is I have collected everything in 1, collected everything in 2. Okay. So, what we have is H1 operating on psi 1 e multiplied by psi 2 e plus H2 operating on psi 1 e multiplied by psi 2 e plus q e square multiplied by the product is what you have. Okay. Now, what is H1 psi 1 e r1 psi 1 e, which is function of r1 theta 1 phi 1. H psi, we know Schrodinger equation, H psi equal to E psi. So, this will be epsilon 1, where epsilon 1 is the energy of this energy associated with this wave function. Okay. And we are talking about helium, remember. So, this wave function is essentially a 1s wave function. So, we write epsilon 1. What about here, and what about the second term psi 2 e function of r2 theta 2 phi 2, it is going to be a constant as far as this H1 is concerned. So, it will come out. Once we have got this epsilon 1 multiplied by this, we can rewrite it in this order. So, quite simple, things we have done many times. Second one also, H2, for H2 this psi 1 e is constant, goes out, but H2 does operate on psi 2 e to give you, once again we can write epsilon 2 psi 2 e, but then epsilon 1 and epsilon 2 are actually they have the same value, minus 13.6 z square by n square eV, same energy as that of 1s electron of hydrogen. Yeah. Why do we get it? Because we are operating a 1 electron Hamiltonian on a 1 electron wave function. Whether we write 1 or 2, how does it matter? Okay. So, this is what we have got, left hand side H psi, right hand side E psi. So, this is your E, this is the energy of the system, and we write the product as a product of two 1s orbitals, one in terms of electron number 1, one in terms of electron number 2. Okay. Everything looks hunky dory so far, then that is because we have so far not thought how the situation gets modified because of the presence of q e square by r12. Okay. That is the problematic part that we have conveniently kept aside until now, but we cannot do that any longer, we have to address it. To address it, the first thing we can do is we can pretend that it is not there. Okay, we have a problem, I mean, I don't, you might know the 7 stages of acceptance of some bad news, or 7 stages of grief. The first stage is always denial. So, right now we are in denial. We pretend as if that q e square by r12 term is not even there, knowing fully well that this is not going to hold water. Come on, you have 2 electrons, they will repel each other strongly, they are confined in a small place. Still, we have to start somewhere, even if it is to prove that this approach is wrong, we have to start. So, we do that. Let us set it to 0 for now. So, this is the wave function, this is the equation you get, very nice. H E psi e equal to epsilon 1 plus epsilon 2 multiplied by psi e, very nice. So, this here is your eigen function, eigen value epsilon 1 plus epsilon 2. We know the values for hydrogen atoms. So, we expect minus 108.8 electron volt. This is the theoretical value that we get using orbital approximation and neglecting this electron repulsion term. The problem is, if you do an experiment, the experiment that is pertinent here is photoelectron spectroscopy. For now we take a rain check on discussing photoelectron spectroscopy. When we talk about molecules, we will have the scope to at least tell you how it works. For now, just believe me when I say that this is an experimental way of determining energy. The energy turns out to be minus 78.99 electron volt, and the theoretical value that we get is minus 108.8 electron volt. Now again we are going to talk about it in a little more detail later on, but there is something called variation theorem which says that your theoretically observed value can never be less, this is negative value, right, stabilization, can never go beyond the experimentally observed value, because experimental value is the truth. This is what Max Planck has said, and I always end up quoting this, it has become a cliche in my courses. Max Planck, the great Max Planck had said that experimental results are the only truth, everything else is poetry and imagination. Not to undermine poetry and imagination, they set human beings apart from other animals, but then science is a pursuit of truth. To do that you must do experiments, and you must do experiments properly, you must not make mistakes, and you must have confidence in your experimental results because they reflect what the situation actually is. Theory is a way of understanding it, reaching it, explaining it. So obviously the theory that we have used is inadequate. We cannot wish this q is square by r12 term away. We have to find a way of accommodating it somehow within the ambit of our theory. How do we do that? Before saying that, let me write this same problem in a little more general terms. For many electron atoms, what is the Hamiltonian? Minus h cross square by 2 mn, this is common. Next we write it as a summation, minus h cross square by 2 me sum over I equal to 1 to n, we are assuming an n electron atom, del I square. So this is the kinetic energy of each atom summed over, kinetic energy of each electron summed over all the electrons. Next we have minus q z n E square sum over I equal to 1 to n 1 by Ri. What is this? This is the sum of potential energy of all the electrons due to their presence near the nucleus. So this term accounts for electron nucleus attraction. Finally we have our problematic term, and it has to be a double summation, because if you take I equal to 1, j can be 2, 3, 4 whatever. If you take I equal to 500, I mean if there are 500 electrons, j can be 1, 2, 3, 4 so on and so forth up to 499, then 501 onwards. So I equal to 1 to n, j, I would prefer to write j is not equal to I. Okay. This is the problematic part. This one as usual we do not worry about, that is a nuclear part, we worry about the electronic part of the Hamiltonian. I hope you see, like we had discussed in the simple helium case, what we have in the first two terms, well the first two summations rather, is a summation of n number of 1 electron Hamiltonians, and the terms that are left over, the summations that are left over, q is square, again double summation 1 by Rij, these are the electron repulsion terms. See, when you have more than 2 electrons, situation is more complex, right. Suppose you have 3, then you have 1 3 repulsion, 3 2 repulsion, 2 3 repulsion. But then do not go back and say you also have 3 1 repulsion, 3 2 repulsion, 1 3 repulsion, so on and so forth. So it is you have to take combinations, not permutations. Okay. This is what it is. So this is the simple form in which I can write it. Cannot be ignored, as we know. These are the inter-electron repulsion terms. So, the only way to go ahead, so hydrogen atom, your free electron, particle in a box, these were all nice systems where we could exactly solve Schrodinger equation, right, analytically. Now you cannot, you have to use numerical methods, and we are going to spend considerable effort in understanding some of the numerical methods, but for now let us study the simplest one. We are working under the ambit of orbital approximation, and this here is our Hamiltonian. What we do is this, we think in this way, and well, there is nothing new for anybody, because this thought process is there from the very early days that you study atomic structure. The thought process is this 1 by Rij, this is basically repulsive interaction between the electrons. Okay. Now what it does is that it offsets part of the attraction each electron feels with the nucleus. Okay. So what we are saying is that the actual nuclear attraction felt by the electron is a little less. Net nuclear attraction is actual nuclear attraction minus repulsion by other electrons. So this phenomenon is called shielding. Okay. Shielding, everybody knows what a shield is, isn't it? So well, when we were kids, Star Trek and all used to be very popular, and there you would hear these people going out into outer space screaming that the shield is down to 50%, shield is down to 20%, it is a protective layer. So what we are saying here is that the shield, each electron partially screens the nuclear charge for the other electron. So 2 electrons, due to presence of 1 electron, electron number 1, electron number 2 does not feel, suppose the nuclear charge is +3, it does not feel +3, it feels a nuclear charge of say +2 or less or more, whatever. Okay. But each electron acts as sort of an electrostatic shield or screen for the other one. Please remember, for the other one. An electron does not shield itself from the nucleus, it shields the other ones. Okay. So that brings us to the concept of effective nuclear charge. I just said it without mentioning the name. I said that due to the presence of 1 electron, the other one feels, instead of 3, maybe nuclear charge of 2.5 or 2 or 1.5 or more or less. So we invoke the concept of effective nuclear charge, which is Z minus sigma, where sigma is called the shielding constant. What are we doing here? This here is our Hamiltonian. First term no problem, second term no problem, third term is the problematic part which we are not being able to handle. So we have conveniently shifted the effect of the third term into the second term itself, into Z itself, because then we can we do not have to write the third term anymore. It is accounted for in this shielding constant. This is how you write it, He equal to minus h cross square by 2 me sum over I equal to 1 to n del I square minus q into Z nuclear charge, effective nuclear charge, E square sum over I equal to 1 to n 1 by Ri. Okay. So this Rij, problematic Rij vanishes. Have we neglected it? We have not actually, we have accounted for it in sigma, but the good thing is that allows us to write our Hamiltonian in terms of terms of n number of 1 electron Hamiltonians with the modification that screening is accounted for. Okay. So for helium atom, this is going to be the Hamiltonian, and your wave function is going to be something like this. The only change in the wave, so remember, wave function will also change. The change is that see, these are 1s wave functions, right. For helium 1s wave functions will be used, but look at this, e to the power minus z effective r. Look at the constant z effective by A0. What does that mean? If z effective is less than z, then this constant becomes smaller. So for any given value of r, psi becomes a little smaller. Also the fall off is not as much as it would have been for full z. Z effective is a smaller number. So the shape and size of orbitals, if you want to put it that way, is going to change because of effective nuclear charge. Now we will just demonstrate using a simple calculation. So let us say that we talk about helium atom as usual. Z effective is 1.69 n equal to 1. So, energy of helium accounting for your shielding turns out to be minus 77.68, whereas the experimental value is minus 78.99. So, is that a good agreement or is that a good agreement? It is a good agreement. There is no scope of saying it is not good. Given the kind of approximation we have invoked, it is as good as it gets. Okay? And the effect of this effective nucleus charge is such that one thing that we need to remember, see for one electron systems hydrogen atom, the 2s 2p everything had the same energy. The moment you put in more electrons, the moment the system has more electrons than 1, 2s and 2p are no longer degenerate, they have different energies. Okay? And shielding of different, and that is because shielding of different electrons in different orbitals, extent of shielding is actually different, and that is why you have this, you know this, very familiar with periodic properties, and that is why ionization energy exhibits this kind of a sawtooth variation, because it is not exactly like hydrogen. Your different electrons in different orbitals, even if n equal to n is same, actually have different penetrations, different shielding. That is one part of the story, electron-electron repulsion. The second part of the story, which at the moment I am in a little bit of dilemma about to what extent we will develop in this course, is that of spin. Spin is something that you have heard, and many of us might have the idea that the spin quantum number arises out of the electron actually spinning on the axis. That is what people thought in the first place. That is why it was given the name spin. However, it is not. Origin of spin, one of the origins is Stern-Gerlach's experiment of 1922, where this beam of silver atoms which passed through an inhomogeneous magnetic field showed two lines, which means that the ensemble splits into there are two kinds of atoms in the ensemble, and the explanation was the presence of two angular momentum states. Remember angular momentum? We have talked about angular momentum at some length, but these angular momenta are different in the sense that they are intrinsic to the electron. If you take an electron inside an atom, then you get NLM and you get S. You do not, I mean you just take a free electron, there is no N, no L, no M, S is still there. But one thing we will have to develop is what is the meaning of S and what is the meaning of MS. I think our earlier discussion of your angular momentum, rigid rotor and hydrogen atom is going to help us big time. So, very briefly we can say that it is not a result of actual rotation, it is written in an unknown coordinate, but interestingly you can talk about its Z component. It really arises out of relativistic quantum treatment that Dirac had performed, and many people still continue with it. So, it is associated with a spin angular momentum S, capital S, and its magnitude as usual is h cross multiplied by root over s into s plus 1, where s is the spin quantum number. Do you see the analogy between this and the azimuthal quantum number or that rotational quantum number J of rigid rotor? Capital J in rigid rotor, L in hydrogen atom, S in spin quantum number, all have identical behavior, okay? And Sz is Ms h cross. Ms, as you know, denotes the Z component of angular momentum. It has 2s plus 1 values as we have demonstrated earlier, same derivation as what we had done for J and M. Now for electrons, spin is half. This is another common source of error. Please remember, for electrons spin is not plus half and minus half, that those are Ms. Ms is plus half and minus half. Spin is half. What does spin designate? The length of the arrow. What do this plus minus half designate? Whether the arrow is pointing up or down. Okay. We will talk about spin at a greater length in the next module, but for now let us conclude here that you have to incorporate spin, and you cannot just write these orbitals in terms of spatial coordinates. When you include spin along with spatial coordinates, then you get modified orbitals that are called spin orbitals. So, the total wave function is a product of spatial and spin parts. Each atomic orbital now becomes doubly degenerate, right. Ms can be plus half or minus half. That is why later on we come to this rule where no more than 2 electrons can occupy each orbital, right. Pauli exclusion principle, that comes because you have only 2 values of Ms. And then please remember, spin orbitals are orthogonal and normalized. So, total quantum numbers that we now have are N, L, M and Ms. Please remember Ms and not S. We went through this last portion a little hurriedly, it was meant to be only an introduction. We are going to develop the concept of spin in little more detail slowly. Okay. Then we will continue with our discussion of atoms with more than one electron.